Welcome everyone to She Has the Floor for November 16. This is our third STEM chat and we have an especially interactive program for today. Today's talk is the link between molecules in space and life on Earth, and our speaker, who you will love, is Rebecca Hirsch. Rebecca is among the scientists exploring the boundaries of outer space at JILA, formerly known as the Joint Institute for Laboratory Astrophysics at the University of Colorado Boulder. We're so grateful to JILA for their partnership, as well as to JILA's Excellence in Diversity and Inclusivity team, also at CU Boulder. Thank you to everybody who's joining, whether you're watching our recording on a private link or you're joining live. Thank you for being here today. Here is an overview, and Crystal is going to share our roadmap for today's program. So here we are. We'll begin with our introductions of our speaker and key members of our team. Then Rebecca will take the floor to present today's STEM chat. During today's chat, she asked that as you have questions, as they come up in your brain, go ahead and post them in the chat during her talk. And then if you have additional questions after she has spoken, you can post questions there as well. Finally, number 4 and last, we will ask for your top takeaways in words and phrases. We'll ask you to place those in the chat, and Crystal will take those away and create a great word cloud of them. And I'll give you a hint that the shape of this week's word cloud will have a link to what Rebecca's talk is for this week. So the hint is molecules. So look forward to that. All right. And now I'd like to introduce my co-host, Bea Petner. Bea earned in her mid-teens a degree in mathematics and then went on to major in fashion design at Colorado State University. After toying with the idea of engineering, she's overjoyed to be in her career as a fashion designer, and we're overjoyed to have her here this evening. Bea?
Thank you so much, Heidi, and so great to see you all. Super excited for today. So first, I'm just gonna reference some of the guidelines in the chat. So in just a moment or two after we introduce the team, we will then ask you to say your name, the grade you're in, and also your favorite subject, just to introduce yourself. So begin thinking about your favorite subject as we near that point. Also, please leave your camera on if possible. Make sure you have a good internet connection. Change the Zoom name if your name is to your name if you're using someone else's account. Mute your sound when you're not speaking. And then, as Heidi mentioned, ask your questions as you think of them at any time during the presentation. So when a question comes to your mind, write it in the chat at that moment. And then Heidi or myself will call on you to ask your question to Rebecca. At that point, unmute yourself, and then you can repeat your name and grade to ask that question. Every question is a good question. Ask what's on your mind whenever you think about it when Rebecca is talking. At this point, I'm really excited to introduce Gail. So Gail Geschwind is someone who loves to participate in outreach programs that make a positive and meaningful impact in others' lives. This is what she did when she helped found JEDI, JILA Excellence in Diversity and Inclusivity, a group which helps promote diversity as an integral element of a collaborative research institute. JEDI functions alongside her work as a graduate student in the physics department at CU Boulder, where she does single molecule biophysics research, focusing on the mechanical and energetic properties of nucleic acid structures. Gail received her Bachelor's of Science in Physics and Math from Stony Brook University, New York. Gail, over to you.
Hi, everyone. Thanks for the introduction. So like Bea said, I'm Gail. I'm a graduate student, and you can basically think of that like I'm in 21st grade. So I went to high school, I finished 12th grade, and then I went to college 4 more years, and then I just kept going to school. So now I'm in 21st grade. And I work at JILA, which is a collaboration between CU Boulder, which is a university, and the National Institute of Standards and Technology, which is a government lab. And there is so much really interesting and diverse research happening here. So we have people studying astrophysics, lasers, atoms, molecules, people making the most precise clocks in the entire world. Just tons of really cool science is happening. And like Bea said, I'm also involved in JEDI. I helped found it, and we work on making sure that there's a diverse environment at JILA, which includes making sure that we get more girls interested in science. So one of our most important messages is that science is for everyone. And I'm hoping that you guys can feel the love of science today. And I know that you're going to really enjoy today's talk, but before we get to that, I'm going to turn it back over.
Awesome. Thank you so much. So at this point, we would love for you all to introduce yourselves. So if you want to unmute yourself, say your first name, the grade you're in, and your favorite subject. So Althea, you want to start?
I'm Althea. I am in 6th grade, and I think my favorite subject is math.
That's awesome. And then the Thomas Campbell, if you guys want to introduce yourselves.
Maisie, you go first.
My name is Maisie. I'm in 5th grade, and my favorite topic is art.
My name is Francis. I'm in 7th grade, and my favorite subject is reading.
Awesome. And then the Jody Whitelock.
So I can't figure out how to change my name, but my name is Lucy. I'm in 6th grade, and my favorite subject is probably math.
And then Jane, if you want to introduce yourself.
Hi, I'm Jane. I don't have a grade. I'm actually retired educator, and my favorite thing to listen to is girls doing their thing. I just am so impressed with you all. Thank you.
Thank you all so much for introducing yourself. And now I am so excited to introduce our speaker for today. So can you relate to the feeling of being surrounded by arts and literature and almost everything but science and math classes? Or maybe you are, but you somehow don't feel like you're really great at it, or you're not excelling as much as maybe you feel like you want to be. Well, that's what happened to Rebecca Hirsch, who started her journey with her eyes set on writing in her arts-focused high school and was surrounded by arts and literature and everything really but STEM, and never thinking that science and math is where she would devote her life's passion. Then in college, she tried agricultural sciences, but still hadn't felt like she'd found her passion. It was at that point in college that she started taking her required general education chemistry 1 class, and instantly that fire lit inside of her and her passion for STEM just exploded inside her. She then made a radical switch in her life to study both math and chemistry as a double major in college. She is currently a physical chemistry graduate student at the University of Colorado Boulder and a member of the Weber Research Group at JILA. Her talk today, The Link Between Molecules in Space and Life on Earth, delves into the learning, processes, outcomes, and other experience on her work on cold, gaseous organic molecules from the depths of outer space, and how these molecules may have played a part in the origins of life on our planet. And now with that, she has the floor.
All right, well, thank you for that introduction, Bea. I'm gonna share my screen really quickly and then present. There we go. All right, so molecules in space is the topic we're discussing today. But before we get to space, let's talk about Earth. I assume everyone here, all of our girls and adults, could tell you that this is our solar system. And this little 1/3 from the sun is Earth. So we live on Earth, which is very exciting. And, you know, throughout the course of your education, you're gonna learn a lot about all the other planets as well. But today, let's start talking about Earth. So what makes Earth special? What makes it different than other planets? Do you guys have any ideas? Yeah, Althea.
Earth has life on it currently.
It does have life. Yes, yeah, currently, and not for that long in terms of the overall time that the universe has been around. Yeah, Earth has had life for just a little bit now. It's very exciting. So yeah, that's really the root. That's what I was getting at. You know what? Gold star. But there are many factors unique to Earth that caused life to form. So let's see, we had Francis, we had Maisie, and we had Lucy. So does anybody else want to think of any other things that are unique to Earth? Is there anything that you've heard about in science or in movies? And no is an acceptable answer.
Lucy, go ahead.
It's habitable.
It's inhabitable by life forms. Yeah, that's getting at the root of it, really. We have an environment here on Earth that is uniquely friendly towards living things. Yeah, that's excellent. All right. Let's talk about how that environment came to be, because Earth has been around for a little while, but it hasn't always been so hospitable. So this is a timeline of the history of the Earth, and it's drawn in a slightly unintuitive way. So here on the right-hand side of the timeline is the present day. So you can see there's, what does it say here? GA, that stands for billions of years, giga annuum. Very exciting. So right here is 0 billion years ago, as in now. And all the way back on the left side of the timeline is 4.56 giga annuum, or 4.56 billion years ago. So that's the timeline that we're looking at. That's how long Earth has been around. So what did Earth start out as? Not very inhabitable. Earth was a liquid blob, not even very spherical at the very beginning, full of very, very hot matter. And you can see it takes, maybe a few million years for Earth to start cooling enough that you start to get a core. And that's sort of the first milestone on Earth's journey. Then there is a large amount of progress. The Earth is cooling, solidifying, different layers are forming within the Earth's core and separating out. And you can see there's basically nothing on Earth except rocks up until, let's see, the Archean period. So that looks to me like about 3.9 billion years ago is the first isotopic evidence for life. And how did they find that? By looking in all the rocks that were buried in the Earth, because that's most of what was there. So 3.9 billion years ago, we start to see the first evidence of life. But the Earth had been around for almost 1 billion years by then. So what did we have on Earth? We had really, really hot matter in all kinds of elements. We had oxygen, we had water, both of those things hanging out, bubbling around in our hot soup of Earth. And it wasn't until, 3.9 billion years ago that life started to form. And we think of life in these really, really early stages as even simpler than the simplest insect, right? Smaller than the tiniest bug. We're talking about, very, very small microbes at this point. So what happened right before the first of these tiny, tiny little life forms formed on Earth in the timeline? It was really a reading quiz. Yeah, Althea, go for it.
It looks like the Earth was hit by a bunch of random things from outer space.
Yes, I love the description of random things because, some ignorant folks might call these meteors, but yes, it is a collection of random space particles hitting the Earth in the late bombardment period that immediately precedes the first little bugs starting to coalesce on Earth. So absolutely, I wouldn't say that this alone is evidence, but it sure seems compelling, right? We have water and heat and oxygen all hanging out on Earth, but life doesn't start to form until we get the bombardment until we get sort of an injection of stuff from space through meteors. So yeah, you know, we'll delve more deeply into that, but that's sort of how scientists think about the formation of life on Earth. So let's hop over to our poll, which we have probably already spoiled, but Heidi, if you would like to start that. Quick summary question. What molecules are required for life to form? We have water, we have oxygen, both water and oxygen, or water and oxygen and other. So cast your votes. And the adults can vote too. All right, we have 4 responses. I would say at this point, you have 5 seconds to chime in with your response if you'd still like to vote. All right, so I assume you guys can all see the results of this post. This is being shared. Yeah, you can see it. All right, so the unanimous winner. Yeah, thank you, Heidi. Thank you, Lucy, for that nod. Very helpful. So the unanimous winner was to form life. Water molecules, oxygen molecules, and other additional random molecules are all required. Water alone or oxygen alone, or both water and oxygen, not enough. You need a little something extra from space. All right, so I am going to close this poll. I think I have the authority to do that. All right, so what came to us from space, right? There are these meteors, there are these chunks of rocks. Sometimes they can be enormous, right? Like the size of skyscrapers. And sometimes they can be very small, like literal gravel pebbles colliding with Earth. And, you know, they come from other planets colliding together, breaking it apart to form rocks, all kinds of astronomical events will form them and send them flying around through the universe. But what's so special about these asteroids, right? Because we already had rocks on Earth. I didn't even put that in the poll, but I'm guessing nobody was going to vote that rocks were what was needed to form life on Earth. So why are these space rocks so important? So an asteroid flying around through space, right? You might think that it's a pretty boring journey, right? Because what is space? It's cold, it's empty, it's big. So what is an asteroid doing? Well, it turns out that yes, space is big and cold and empty. All of those things are true, but it's not as empty as you might think. There are very small collections of gases randomly distributed throughout the universe, throughout space. And as asteroids are flying through the universe on their random paths, eventually maybe lucky enough to collide with Earth, they blow through these gas clouds and they occasionally pick up little gaseous molecules. So these molecules can be things that you might have heard of, like ammonia or methane. These very small, simple molecules that are just floating numbly throughout space, eventually can hitch a ride on an asteroid and wind up on our planet. So what are molecules? That's kind of where you should be at this point in the journey, if I've convinced you so far. So molecules are these very interesting things, right? They're very small. You can't see them with your eyes, ever. Anything that's big enough to be seen by your eyes should not be called a molecule. So it's really hard to conceptualize of a molecule. With that said, if you can't see it and you can't really hear them, sometimes you can smell them, but that's, that's pretty abstract. So here on the screen, I tried to give you 4 visualizations, interpretations of what molecules are like. So molecules are made of atoms, which are even smaller and even harder to comprehend. But you'll probably be introduced to them if you haven't already in school. I mean, you guys seem like you're really on top of it. So maybe you've already seen a periodic table where you see all these letters that are atoms. And so here's a visualization where, again, you just see letters, C and H and N and O. So those are trying to represent atoms, which are the individual building blocks of molecules, here being combined into a big molecule. So this is probably a molecule that is too big and too complicated to be found in space, but it would have been present in sort of the early formations of life on Earth. So this is kind of the size of things that were hanging around when the first prebiotic bugs started to crawl. But this is a pretty boring visualization. So you might enjoy something with a little more color. You can still see here we're identifying little atoms and they're kind of holding hands. Oh, I did that. They're kind of holding hands. And this just shows you a little bit more distinguishment, right? So these little H atoms over here, they're blue in this representation, but they're really small. And if you look really, really closely, this visualization actually shows that this O atom over here in red, this oxygen atom, is actually a little bit smaller than this C atom in the middle. So it gives you a bit more of a sense of the personality of these atoms, right? Hydrogen, teeny, teeny, tiny. Carbon, little heftier. And oxygen, just a little bit smaller than this carbon atom in the middle. And carbon and nitrogen are pretty much the same thing. So yes, there are lots and lots of different ways to visualize and try to understand molecules and the atoms that make them up. But I just wanted to give you many visual representations to show you that atoms and molecules actually have some pretty unique personalities. Hopefully you can see that here in these highly scientific representations. All right, so molecules, teeny, teeny, tiny, right? How on earth are we going to learn about them, especially when they're not actually on Earth, right? We want to know about the molecules, right? The tiny little gases floating around in space that hitched a ride onto asteroids, came to Earth and formed us. So those are molecules that are way, way out in the middle of the universe. How are we going to learn about them? Well, the answer is on the screen. Does anyone happen to recognize this particular object in this picture? It's a little bit famous.
Althea?
Is that the Hubble Space Telescope?
It is the Hubble Space Telescope. I would never have guessed that at your age, but yes, it is. So yeah, Hubble was a pretty famous astronomer. So when we through this big fancy telescope, which is all that the Hubble Space Telescope is, when we put this big fancy telescope into orbit around Earth, we named it after Mr. Hubble. So the Hubble Space Telescope is orbiting Earth, and like all telescopes, it lets you zoom way, way out into the distance and look at things that are far away and make them seem big. One of the perks, or one of the really fancy things about the Hubble Space Telescope is that being out in space, it's far away from the light pollution of Earth. And so it can see things very cleanly and crisply, even when they're very far away, like the molecules that we want to study. So the Hubble Space Telescope, among many other telescopes, is the tool that scientists use to look at molecules. But you know that when I say look, I don't mean literally see little molecules hanging around in space, right? Because they're too small. You know, you can have as fancy of a telescope as you like, but you're never going to get a direct visual of what a molecule looks like. We have to use indirect methods to understand them. So telescopes, like the Hubble, collect light. So if we're using light hitting a telescope to see molecules, what kind of light are molecules sending us? It's not visible light, right? Molecules are too small to have like a discernible color. But molecules send us infrared light, right? Which feels like heat, and ultraviolet light, which gives you sunburns. They send us tons of other kinds of light besides necessarily the visible light that you would expect when you see a picture. So how are molecules making this light? Well, since you guys are expert scientists, you probably are aware that light is just a form of energy, put really, really simply. So the light that molecules send off is just a product or a result of the fact that molecules aren't just sitting there in space. They have energy, right? They have enough energy to be doing a little bit of activity, even though it's very cold and they're very bored. And most of the time they're just hanging out. Molecules, as you can see on this very, very simple representation, have a lot of activity going on. So this is an example of water is really what they're trying to represent here. So you have your oxygen atom in the middle. This time they decided it was black and not red. And then you have your little hydrogen atoms, right, that make up your H2O in water, hanging off the sides of this oxygen atom. So here you have water with a variety of dance moves, is really how you should think about it. The light that we see water in space sending to our telescopes is really just a result of the energy that that water is putting into its variety of dance moves. So if you guys would like to join me, it is now time for our dance break of the session. So we're going to start with some symmetric stretching. Oh man, I have to be so small to fit in my screen. But symmetric stretching, one of water's favorite dance moves. It's a classic. Everybody loves it. There's also anti-symmetric stretching. You can go either way. Yep, it's a good one. A little trickier. All right, there is rocking. This is my elbows are the oxygen. There's rocking. There's plenty of rocking in water. Yep, excellent, excellent. There is wagging, which is very hard for me to represent. We can do a bit of a little wag, however you interpret, because water doesn't have arms. So there is twisting, which sorry, I was getting into a little bit there, but twisting, one of water's favorites. And our last one, scissoring. All right, so are you guys feeling toasty at this point? A little heat? Yeah, you got a lot. Lucy's ready to go forever. So yes, so I would say that we have now demonstrated that you burn a lot of energy by doing these molecular dance moves, right? So for molecules, that energy is shot off into the universe as light, and our telescopes are there to look for it. So this is how molecules in space interact with our telescopes. Very exciting. So then how do scientists on Earth take those, those energies, right? Those different amounts of energy that molecules are sending us and figure out anything from it? Well, this is a much more boring image than the last one, but this is the sort of thing that as a scientist, you get to look at and decipher and interpret. So on this graph here, we're seeing how much energy at what particular amount of energy is being sent by this water molecule. So you can see they labeled it. So here is, well, it's actually much more complicated. But here, for example, little lump A here at maybe like 3,400 units of energy. there is a bunch of light of that particular amount of energy being collected by our telescope. So what does that amount of energy correspond to? In this example, it's the symmetric stretch on water. So the hydrogen's moving away from the oxygen atom. That's what's being shown here on this graph. When we talk, when scientists look at it, they're able to convert, the idea that there is about 3,400 units of energy here. And they know that 3,400 units of energy on this water molecule is a symmetric stretch. So it's very cool. So if you had a graph like this, and you were a well-trained scientist looking through your telescope, you would be able to see that where you're pointing your telescope, there is water. There is something with an oxygen and a hydrogen, and it's doing a symmetric stretch. So that's how we can identify, we can interpret this sort of abstract data into real concrete things like molecules wiggling in space. Okay. So there are many more things than water out there in the universe. One of the things that scientists are starting to consider more deeply is that molecules, much like the ones that you see on this screen, were probably primarily responsible for life forming on Earth. So these molecules here, they don't look like water, right? There's a couple things that I want to point out here. So first of all, these molecules, which unfortunately in this very artistic screenshot, you can only really see all of one, but you can see a lot of the other ones. They're floating around in space. So a couple things that I want to point out here. First of all, in these molecules, all of the atoms that they're showing here are exactly the same, right? They're all the same size. They're all the same color, which is a very useful tool that we use when we're trying to make sense of molecules and atoms. So here in these molecules, they all seem to be made up of the exact same atom. And in this case, in this representation that this scientist is trying to show here, that atom is carbon. So every single blue blob that you see in one of these really pretty lattice molecules is carbon. So this is just carbon shaking hands with carbon, carbon, carbon. I don't know if you guys can actually see my mouse, so that may not have related to very much. But yes, these are molecules entirely made up of carbon. The other thing that I want to point out is that the shape that you see all of these carbon atoms coming together to form is a hexagon, right? A six-sided, well, not circle, a six-sided polygon, a hexagon. So all of these carbon atoms are in this very stable, happy hexagon. And a couple hexagons link up in space, and pretty soon you have a big molecule, like this guy over here, or even this big old sheet of hexagons that you can barely see in the background. So this is the kind of molecule that scientists are starting to really consider as the primary molecule that hitched a ride on an asteroid and came to Earth and combined with water and oxygen and other small molecules and heat to start to form the basic beginnings of life. So what do we do here? What do I do besides just talk about molecules? So my job as a scientist is to build tiny little copper boxes like this one that inside of which I simulate space. So space is mostly empty, it's pretty big, and it's very cold, right? So if I want to simulate space, I have to remove pretty much all of the air and all of the gunk that would normally sit inside of this copper box. So I do that. I have a pump, just remove all of the molecules that would normally be hanging out in a copper box on Earth. And then I cool it down. So I am able to cool this box down to about 4 Kelvin, which is approximately the temperature of the majority of space. So I have now a very cold, very empty box. And then I'm able to inject into it a few molecules, mostly molecules that look like this, right? That are small collections of carbon hexagons. So I inject them into this box, they float around, they cool down. So now it's as if these molecules are floating around in space, right? They have exactly the same kind of environment and energy and interactions that they would have in space, but they're here in my very nice little box. So then I'm able to send in a laser and observe the light, observe the energy and the motion that these molecules have in space. So with that kind of experiment, I'm able to sort of make, or my goal is to make a sort of database that, you know, if I have this molecule and it's floating around in space, I should be able to tell based on that experiment that I did in my very cold copper box. I should be able to tell exactly what kind of dance moves this molecule would perform when floating around in space because I've simulated it on Earth. All right, so that is the end of my talk. I think we're going to leave it open for questions for a little bit if you guys have any.
Yeah, so do we have time for one quick question? If we have one question from an audience member, and just remember, every question is a good question. If you want to raise your hand or pop it in the chat or just unmute yourself. Yeah. So Althea, if you want to unmute yourself, it looks like you have a great question.
What type of molecule is the one that's just blue hexagons, just carbons?
So let's see, let's go back. So this one that you can see, it is 7 carbon hexagons all just sort of stuck together, so that it forms an even bigger hexagon, right? This one is called coronine, and it's actually one of the first ones that I looked at. But there are many molecules in space that are just like this one, but instead of having 7 hexagons smushed together, they might have 10 or 1,000 or 2. So this category of molecules where it's just a bunch of carbon hexagons are called PAHs, polycyclic aromatic hydrocarbons, and they are very cool. They include things like graphene that you've probably heard of, right? Like graphene is this super amazing material, and we're going to build everything out of it in the future because it's so conductive and it's so strong and all of these great things. Well, that's just a big, it's a big PAH. It's a bunch of carbon hexagons stuck together. But yeah, this one's corny.
We have a question from Jane Hamburger as well. Jane, why don't you go ahead and ask Rebecca your question?
I was just wondering why you chose copper to be the material your box was made from.
One of the important questions is the fact that it is relatively cheap and very available. But, you know, so our sort of common metals that we work with to construct things in labs are, you know, copper, steel, aluminum. Those are at least my 3 go-tos. Gail might have a wider variety than I use, but that's sort of the set that I work with. And of those 3, copper has the best thermal conductivity. So it is the easiest to remove heat from copper, or it's easier to remove heat from copper than it is from aluminum or steel. And the most difficult aspect of this box to get right is the temperature. So we wanted to use a metal that would be very easy to suck heat from and get it very, very cold. that was why we often use copper.
Great practical question. Thank you, everybody. I want to encourage everyone now to use the chat and pop in there a word or phrase that represents your favorite part of today or your favorite takeaway. And you are welcome to put multiple responses in there. So everybody jump in there, log your favorite takeaway from today in a word or phrase or several words, a string of words or phrases. And again, Crystal, our tech director, will take those away and create a really great word cloud.
And while all of those amazing words and responses are coming in, I'm going to just jump in and begin to announce the next few things. So we hope to see you back here on November 30th for the importance of perseverance. Our speaker will be Beth Kroger, Chief of Staff and Chief of Operations at JILA. And a huge thank you to Rebecca, to JILA, JEDI, and for every girl and family member who attended, whether live or watching this recording. And I'll pass it back to Heidi for a few other final thoughts.
We're entering our season of giving, and we're so thankful to everybody for helping us make this very first She Has the Floor season such an engaging and interesting time together. We have a bonus session coming up for you December 31st. We've had such good response from girls and parents and the community that we will be doing another session in 2022. But for this fall, we're adding on one more additional bonus session, December 21st, and we'll tell you more about that next time when we meet on November 30th. Our tech director and manager of marketing, data, and analytics is Crystal Bordner. Our content creator is Kenna Castleberry. Our diva for social media is Amber Cruz. Our number crunchers are Jessie Ann Lee and John David. The ambassadors for Pretty Brainy are Katie Shutt, Madsy Boyles, and Emma Younger. Girls, if you're able to get on social, connect with our ambassadors. Our board members are Mina Bogopal, Dawn Putney, and Robin Steele. And our wise women are Jane Hamburger, Marianne Heyman, Ann Clark, and Pat Smith. Thank you to the Deaver Phoenix Foundation. Thank you, HP. Thank you to the Society for Information Management, the Community First Foundation, Women in Science at Colorado State, Payroll Vault, and Prima Productions. Thanks to all of them, we're able to do great programs like this. That's it for this evening. Thank you everybody for hanging in there as we went a little long. And just a reminder that we'll send the word cloud to you, as well as the link to the recording for today's session. Have a fabulous Thanksgiving. We'll see you November 30th. Bye-bye.
Thank you.